Hello guys, welcome to Backbencher Studies channel. In the last video, we discussed how we can find the stability of the system based on the location of poles or the roots of the characteristic equation or characteristic polynomial. So in all cases, we cannot find the all the roots of the characteristic equation because the characteristic equation of is of higher order, say s power 6 or s power 5, then that will be a chaos to finding all the roots and stuff. So in that case, how we can find the stability of the system, that would be would not be possible just by solely finding all the roots and thereby locating all the poles and thereby seeing whether all the poles are in left half plane or in right half plane or in on the imaginary axis. That would be a too long procedure to do that, and that would be a complex mathematical calculation as well. So to do so, we should not we cannot find roots for a higher order polynomial just by simple mathematics. So how in that case, how we can categorize that this system is stable or this system is stable, unstable, marginally stable, like that. So for doing that, we have one stability criteria which is called Routh-Hurwitz stability criteria. So it is very a powerful tool in determining the stability of the control system just by knowing the characteristic or equation of the closed loop transfer function. So it states that the number of roots in right half plane of S. So in the S plane, the number of roots in right half plane which makes the system unstable is equal to number of sign changes in first row of Routh array. So this Routh array is kind of made of the coefficients of the polynomial equation that we will be discussing in this lecture here over here. So we have to create the Routh array for a given polynomial, and based on the first row of this Routh array, if we see the number of sign changes, that would be the number of roots in right half plane of S. So if we have a single sign change also, then we have one right half plane pole which makes the system unbounded and unstable. So let us start the Hurwitz stability criteria. Let us apply our knowledge, and based on that, if we are given with a characteristic equation closed loop system, then how we can find the stability, how we can comment about the stability of the system. So let us start. So this is the characteristic polynomial which is given, which of order n. So we have the coefficients of this characteristic polynomial an s power n plus an minus 1 s power n minus 1 plus an minus 2 s power n minus plus on a0. So similar kind of thing. So we need to find out the Routh array for this polynomial first. So how we do that? We can do that by writing the highest power over here. So s power n will be the highest, and s power n minus 1, s power n minus 2, and up to s power 0 we need to write that. And s power n coefficient should be written over here, and alternative coefficients of these polynomial should be written in this fashion. So we have an, the coefficient of s power n in this Routh array, and next alternatively we have an minus 2 written over here, and an minus 4, and so on up to the s power 0 coefficient if this s n is even number. If this n is odd number, then we are left with this s a2 coefficient. Then Similarly, we can write s power, so for s power n minus 1 coefficient, from starting to that we need to write alternate coefficients just like that. So these bn coefficient and bn minus 2 coefficients are found out by these coefficients, these first two rows of coefficients. So that's how we can find out the remaining coefficients of powers of s power n minus 2 like that. So let us see how we can find out these coefficients based on these coefficients alternatively taken in Routh array. So Bn is the multiplication of these two, An into An minus 3 minus multiplication of these two, An minus 1 into An minus 2 divided by this coefficient over here, An minus 1. So that's how we calculate Bn, and Bn minus 2 is calculated as we have to multiply first the, these two coefficients like an minus 1 into n minus 4 minus these two coefficients product an into n minus 5 divided by this coefficient, that is what Pn minus 2 is. So in the similar fashion, if we multiply this and this, and if we subtract this and this, then by thereby dividing with this value over here, we will get Bn minus 4 as well. So this is how we compute the Routh array, and s power n minus 3's coefficients can be computed with these two rows, with second and third row of this Routh array. So this is how we can create the entire Routh array based on this rule. And if we have to see the sign changes in this first row. If these sign changes are zero, then our system is stable. So this is the formula for Bn. So let us solve a question that would be much more clear. So here we have a characteristic equation given: s power 4 plus 2s cube plus 6s square plus 4s plus 1. So we have to first create the Routh array. So this is how we can create. So the highest power is s power 4, and lowest power is and next power is s cube, and we have to make this s square and s power 0 up to all the way up to 0. So the coefficient of s power 4 is 1, and from here we have to write alternate coefficients. So we have 1 and 6 and 1 over here. So 1, 6 and 1. And s cube, we have the coefficient of s cube as 2, and alternatively we have the coefficient here as 4. So we can calculate the next coefficients by this formula over here, just like that. So let us calculate that. So 2 into 6 minus 1 into 4. So 2 6 are 12 minus 4. 12 minus 4 is 8, and divided by this coefficient by 2 means we have 4 over here. So that's how we can solve b1 and b2. So if we add that b1 and b2, we have 4 and 1 over here. And if we kind of like if we find out the next row of this Routh array, which is the power of s, then we can solve that. 4 into 4, 16 minus 2 into 1, 2, 16 minus 2, that would be 12, and 12 by 4, that would be 3. So sorry, the 16 minus 2, that would be 14, and 14 by 4, that would be 3.5. So that's how we can solve the 3.5 over here. And we don't have any coefficients over here, so we won't be having any coefficients over here as well. So then we can find out the s power 0 coefficient, which is 3.5 into 1 minus 4 into 0 by 3.5. That was giving us 1 over here. So we have one over here in this Routh array. So this is how the Routh array is completed. And if we see this first row of this Routh array, we can see that they all of them are positive. There is no sign changes from here to here positive, no sign change, and here to here positive only, no sign change, no sign change, and no sign change. Thus we can say that this system with this corresponding characteristic equation is stable. So this is how we can apply the Routh-Hurwitz criteria. Thank you guys. Thank you for this amazing session.